All right, so I think, yeah, I'm going to start this chapter 5 of the book. It's about DC converters and the applications that we have there. So let's start with the system description, general description that we have for the problem. Here basically we have some two sides again, that both sides we consider to be DC in terms of form of electricity, but we do not specify what they are. They can be single units or a combination of units or things like that. And then we have a converter here, voltage source converter, right? Single phase voltage source converter. I think in almost all of my simulations I use full bridge converter with unipolar PWM. We have a capacitor here on this side, and then we have a filter here on this side. Okay. So what is the general statement of control objectives in this system? This is the controller basically that receives some of the measurements, local measurements. We do not really rely on non-local measurements. All measurements are local at this level, and there are some set points, and then the controller generates the switching times for the switches inside the converter. So we would like to track the set points, right? So again, we do not specify at this time what are those set points, but whatever the set points are, we would like to track those set points. Power or current. Common set points are power, but it could be other than power. Right? So I use set for the set point. So when I say P set or V set or I set, that's basically set point. Now, one thing I think I briefly mentioned, or I forgot to mention in the chapter that we're talking about power electronics, and that's very important about power electronics. If you do not consider that, you are missing a very important aspect of power electronics, and that is this aspect here. Now, power electronic switches have this limitation, if you want, that they cannot tolerate a current much larger than the rated value. So they have very limited capacity beyond their rated value. If their rated value is 10 amperes, you really are not supposed to expose this switch to more than 12, 13 amperes. Maybe very short transient, it's alright, but not for any extended time. You cannot really expose. This is a major difference between power electronic devices and the standard machines that we have. Machines with windings, they don't have this limitation. Generators and motors, both of them. They can, in a transient mode, they can tolerate huge amount of current, often several times larger than the rated value. But in power electronics, it's only a fraction of the rated, not even 1%, not even 100%. Okay. So 20%, 30%, 40%, things like that. So for that reason, one of the objectives of the control system, we put that there always, is that to make sure that the current flowing into these switches here do not exceed that limit. Because if they exceed, they will damage the switch. And that is a control. We will see we can do that using control. So we put that as a control objective. So, and then provide support. This is again an aspect that we go into details of that as we go on more and more. Inertia and other types of support to the power grid, or to, again, to what? whether to the other side, to this side, or this side. Support can be provided by this entity to this side or to this side, both of them. So if this is grid, for instance, and this is a source, PV, and you want your PV to provide support to the grid, that's called it a grid support. Normally it's grid support, but it could be the other way around also. You want to provide support to this voltage. So again, as we go on, depending on the problems that we have, we will specify what we mean by support. And then this is the thing that we always talk about, robust, remain robust. If you have parameters that are changing, or if you have disturbances coming into the system, the control system, the feedback control system, now we all agree that we need to have a feedback. We cannot go without feedback. So the feedback control system must be able to handle those uncertainties and those disturbances. So I think this is a good summary of really, or general summary of what control objectives are in this system. Okay, like I said, solar photovoltaic system is a special case here because it generates DC. So I have spent a few pages, not too much, just to briefly explain how a solar photovoltaic system generates electricity and the converter works for that. So photovoltaic effect is the generation of electric field in a material upon exposure to light. Okay. So that's the property that some silicon material have. If you expose them to light, the electrons in these layers, they can absorb the energy from the solar lights, solar rays, and then move to higher levels of energy. And then eventually, if they can become free and then go outside, that becomes flow of electricity. In other words, if they can absorb sufficient amount of energy so that they become free, they can just move outside, there will be electricity. If they can just move a little bit and they cannot become free, they may come back and lose their energy as heat, or just stay at a higher level of energy. So this phenomenon is called photovoltaic phenomenon. Solar cells are really the core material, the core blocks that generate solar energy. So these are typically this type of thing. So the small solar cell here is, and then you put solar cells together and then generate a module, and then put the modules together and you can generate an array of solar cells. One individual solar cell is, but first of all, the conversion efficiency is for the commercial PVs, not for fancy PVs. For commercial PVs is 13 to 18%. So out of the energy that comes from the solar rays, anywhere between 13 to 18% will be converted to electricity. The physical thickness is between 0.25 to 0.35 millimeter, and the surface area 100 to 225 square centimeter. Okay. So depending on how much solar ray is radiating on this unit, it generates an electricity. Let's say, and that solar radiance, the strength of that solar radiance is basically quantified by what we call solar irradiance or insolation, or just simply irradiance. So at the solar irradiance of 1 kilowatt per meter square, which is really a strong sun, and the temperature of 25 degrees, a solar cell can produce a current between 3 to 4 amperes at approximately 0.5 volt. So if you multiply together, you're talking about 1.5 to 2 watts for one solar cell. And that solar cell is, the size is this one, 100 to 225 square centimeters. So you can imagine how much that size of that cell is. Now put them together, and then you can come up with a solar panel with 200 to 300, 250. Nowadays we have higher power panels. and then the voltage of 3 to 40 volts and current of 6 to 7 amperes. Okay, so the solar panel or solar cell have a characteristic like this. When we say characteristics, there are two characteristics that are very important for the solar cells. One is the current voltage and one is the power voltage. So the current voltage is like this. It's pretty much flat when the voltage is small, and then kind of sharply drops to 0 when the voltage increases beyond some point. And if you multiply this one into the current, you will get this characteristic here, this red one, which is the power. So it starts at 0, goes all the way to a peak value, and then goes back to 0. Because here current voltage is 0, here current is 0. So you will immediately see that there is one single point that the maximum power happens, and there is one single voltage that if you bias the panel at that voltage, you are able to extract maximum power from this solar panel. So this is called short circuit current, this is called open circuit voltage, this is called maximum power voltage, and so on. And this is maximum power. Okay. More definitions about irradiance and other things you can find here. Now, this characteristic is a function of two main parameters. One is the irradiance. Obviously, if the sun is stronger, the current and the power are more, almost linearly. You see, when you go from 600 to 800 to 1000 as far as irradiance, then the characteristic goes up and the power goes up almost in proportion. Another one which is less change compared to this one is the temperature, and then when you increase temperature or when you decrease the temperature, what happens is that the voltage now goes up. The open circuit and the maximum power voltage goes up. The irradiance changes the current, the temperature changes the voltage. And at lower temperatures you get larger powers at larger voltages. Okay, these are models for the solar panels. They used to be very useful before. People use these models for simulations and other things, but nowadays any software, almost any software that you go to, like Simulink, PSIM, Plexim, all these software have built-in solar panels. So there is no reason anymore to use these models unless there is a research or analysis that you want to really do some calculations. So you can use these models to do that analysis. But as far as simulations, you have access to plenty of different solar panels from all different companies in these software tools. If you go in MATLAB, I think you have a library of about 1000 solar panels. So you can choose what solar panel from what company and then bring it there and put in your simulation, things like that. Okay. So for PV, we have generally two topology of converters. One is two-stage and one is one-stage. So two-stage, you have a first stage here and then you have a second stage. So the first stage connects the PV to an intermediary link. We call it normally DC link because in AC systems its other parts are AC, but this part is DC. But anyway, we can use the same terminology here. This is called the DC link or intermediary link, and this is obviously the voltage across PV, and this is the grid side. It could be grid or load, but for single stage you do not have this intermediary link here. Okay, so these are two topologies that we have. I mean, I have talked about maximum power point tracking and other things, which later on we go to that in more detail, so probably it's not necessary to explain here. Okay, so after this very brief explanation about PV, we could go back to the original problem that we had, and later on I will bring PV back later in this chapter. Okay, power control. This is really the common approach of looking at this problem. Power control via current feedback loop. So we want to control power, that's the objective. However, we do that through a current feedback loop. And the reason we do through current feedback loop is because this facilitates or gives us the flexibility to limit the current. If you don't do that, you will have hard time limiting the current. So this is really the most common approach. Okay, so this is the, let's say, start with this single stage here. So we want to control the power. Again, to make it simplified, let's say the power flowing from this side to this side, but doesn't really matter if it's flowing from this side to this side. You may consider that as a negative, or yes, no problem. So that's the power. We want to control how much power flows from this side to this side, or this side to this side, right? So when we say power, if the power at this point we consider, that will be I into Vg here. If you consider the power here, it will be I into V. There will be a slight difference between the two, but not significant difference. It's only a matter of power loss across this resistor, which is not, it's not supposed to be any large number. Or the power on this side, doesn't matter. So for that reason, there seems to be no ambiguity here about where you define the power. With little infinitesimal difference, you can define it here or here. Here is more convenient because Vg, the voltage here, if it's a grid voltage, normally it's fixed and it's given, so it will make the analysis and the design easier. Okay, so now let's redefine the control objectives in this problem in more a specific way. We want to control the amount of power to be equal to P set. Okay, and we want to maintain this objective robustly. Robustly means if parameters or variables in the system change, disturbances or parameters, L, R, Vc, Vg, the control must be robust. And when you apply a command, let's say you are operating at 10 kilowatt, you want to suddenly decrease the power to 9 kilowatt. It should respond quickly without oscillation. That's a good tracking. And the starting transient should be smooth. Again, this is one of the aspects about power electronics. You will see, I will explain that if you do not design the controller properly and you do not consider this aspect particular attention, your converter never starts in practice. Anytime it wants to start, it will shut down. So the starting transient is very important. It should ride through the grid disturbances and faults. Okay, what does this mean? This means if this voltage here experiences disturbances, and that is something that happens all the time, especially in AC grids that we have. So the converter should keep working and ride through the transient faults and limit the current. This is what we said. You want to limit the current of the switches between minimum and maximum and provide support to the grid. So it's connected to the grid on this side and has a voltage Vg. That voltage may change a little bit or may suddenly drop if a fault happens. And our objective is to keep feeding power to the grid, but at the same time provide support to it. And that support is dynamic and static support. I will give you details of this too. Don't worry about that. So, control approach. This is the model of a what? A single phase full bridge, yeah, converter. Agree? Okay. If you want to have bidirectional, we need to use VSC. So the control model for that system using a PWM is this, whether you use unipolar or bipolar. That is this one. So this voltage is the voltage on the DC on the left side, this voltage. Okay, so now I spend a few minutes explain how people conventionally solve this problem. It's a simple problem, nothing really complicated about this problem. And how to solve this problem, the common way is, because we want to remove the steady state error, so we put an integrator here. And S plus Z, obviously we put a 0 also there to be the most general. So it's a PI controller. And then we want to follow P set. So you divide P set by the grid voltage. That gives you the reference for the current. And then reference for the current minus the actual current passed through this PI. That gives you the modulation signal. Very simple. Let's design K and Z. Yeah, it has two control parameters, K and Z. The common approach, okay, before designing also, I think I talked about two aspects here. Let me see how I did. Okay. For current limiting, now we need to limit this part, right? Now, if you really want to always follow P set, you need to divide P set by the actual value of the grid voltage. And when you divide it by the actual value of the grid voltage, the reference of the current goes up. When the voltage, grid voltage goes down. And that's here in this system, this is the scenario that you ask the converter to generate a lot of current. So in order to prevent that from happening, you put the limiter here between min and max, and then put, this is the way to limit the current. So we limit the reference of the current, and if the control is fast, it will limit the actual current. Okay, so that's about how we do the current limiting. Soft start that I mentioned, but I did not explain in details. Let me explain a little bit what the problem is. Okay, if you want to see what is the problem that I said the converter normally has difficult time to start, is that let's say the grid voltage is given. It's a voltage, 400 volt, 200 volt, whatever. So that is here. And then you start the converter. Obviously, when you start, the current is 0. And here, the tracking error, depending on whether it's 0 or non-zero, anywhere, it's a number here. But there is an integrator here. So this is 0, and it takes time to come up. So initially, this is 0. But this is a large number. So if you subtract these two, you will get a large number here, negative large number. At the converter, so this is the voltage across the inductor. So across the inductor, at the beginning, when you start, you have a large negative voltage. And that means a large amount of current will rush through from the grid to the converter. If you just start at 0 without doing anything. If you do not take any consideration, just start as it is, a large amount of current will rush into the converter, and if the controller is not strong enough to suddenly respond to that huge amount of current, it will shut down. The protection system will shut down the operation. So that's the starting problem that the converter has. Now we can fix that problem using control. If you want to fix that problem using control, you need to start at this point with a number that when you multiply into VC, that number here becomes equal to this one. Then it smoothly starts. So just add one single number here, you see, VG0, VC0. If you measure them, you can put the 0 values. If you don't measure them, put the rated values. So when it starts, now this is 0, but this will be equal to Vg over Vc multiplied into Vc, that it becomes equal to Vg, this point. Vg minus Vg becomes 0. So at the start, across the inductor is 0 voltage. It will not have a starting problem. It will start very softly. Okay, so that's the soft start aspect. Okay, so basically this is now the entire control system that we have with the soft start and current limiting here, soft start here, and the controller has two parameters, K and Z. Let's see how to design K and Z. One common approach using transfer function that people use, a lot of people use, they say let's choose this Z equal to R over L. In this case, this pole and this 0 will cancel each other, and the cancellation is on the left side of complex plane, so it's not a big problem. It's not instability problem, because R and L are always positive. So then the advantage of this, so if you cancel this one with this one, then 4 or 5, something like that. So for 5, for instance, K will be 0.01. This is probably the fastest response you can get from this converter. So if you go with that, the response will have a time constant of 5 switching cycles, which is 1.25 milliseconds. So the response is like that, and I will show you the simulation later. So the response, when you apply the command, let's say you apply the command of current from 0 to 20 amperes, it goes like that, and the time constant, if you look at that, it should be 1.25 millisecond. And this is the carrier waveform, and this is the modulation index. See, the modulation index is a number, and then eventually is also a number close to that, 0.4, 0.425, you remember? But when you apply the command, instantaneously it will increase but then decrease it. So instantaneously increase but then decrease it back to a number close. So from 0 amperes to 20 amperes, the modulation index changes only slightly. Okay. Now let's design the same controller using LQT, or linear quadratic tracker, that we just discussed earlier in the previous class. If you want to use that one, you need to, the system has one state variable, that is the current. Okay, very simple. So you multiply into this K, and then you put one integrator, and then you multiply into another K, and then add them together. Right? That's basically that block diagram that we discussed at the end of the previous class. So how to find K1 and K2? You can write the equations of this one and this one, put them together, and then solve the optimal control problem. So equations of the first one, equations of the plant, and then put them together and apply this operator to remove all those DC variables that you don't like them, and they actually cause the problem to not become LQR. So you will end up at these two equations, and your state feedback is negative K into Z. So it's a standard LQR problem. And more importantly, the first variable Z1, which is derivative of X1, is equal to tracking error. We proved that before, but here is also clear. And Z2 is derivative of X2, which X2 is the current. So rate of change of variation of current. And W is rate of change of variation of the modulation index. Okay. So now we can minimize this cost function, which is square of the tracking error multiplied into Q plus W squared. So you choose capital Q equal to Q and 0 because we did not give any weight to the current. Let's say tracking error. Our objective now is to minimize the tracking error. The current, as long as it's within the limit, it's all right. And the limiter keeps it within the limit. Okay. Now I will explain later as we go on how if you add another Q here in the second one here, what happens. So you solve LQR. Okay, and then if you add another Q, that's what I explained here, that will be this one. So this will be the tracking error, this will be the derivative of the current. Now, if you increase Q, let's say from 10 to the negative 5 all the way to 10 to the power of 0, and then observe the poles or eigenvalues of A minus BK, which is the closed loop poles, you will see they move from right to the left along this path. So it's almost along the path of 45 degrees, which engineers who work in control, they know along that line is a very good change. It's optimal. Right? Because it gives you zeta of 0.7, which is overshoot of 4-5%. But we did not impose it here. It turned out to be here. Right? We did not impose it. But because it's optimal, it found it. Right? And if you want to see what happens initially, it is this one, 10 to the negative 10 to 10 to the negative 5. One of them is 0, one of them is negative 6. They move towards each other. And then, so now, if you say, I want to add Q2 and see what happens. So you increase Q, and then at this point, you stop increasing Q and start increasing Q2. Then you will realize the poles move further down. In other words, it will be even more damping. If you are saying, I'm interested to give some weight to the current also, and make sure that changes or oscillations in the current, I want them to be lower, then you can increase Q2 and the system will even damp further beyond 0.7. And if you continue, this happens. So this is the general picture that you will get in a system like that. Okay, so now let's say we increase Q all the way to this, and then increase Q2 to come here. They are at now negative 800. And the pole of the transfer function that we just discussed was also at negative 800. So I deliberately stopped here because I want to compare them together. So I stopped at similar transient response, or similar time constant if you want. And K1 and K2, one of them is 10, one of them is 0.0197. Okay. Now, look at the responses here, and let's discuss this diagram and see what is happening. This is the blue one is the response of the PI controller that we discussed, and the red one is the response of this optimal controller. Here is when you apply a command from 0 to 220 amperes. The PI goes up, the LQT goes a little slower with some reluctance, but it goes up and eventually gets there. And the time constants, or at least the settling times, are close. But here is the thing. Now apply two disturbances to this system. This disturbance in the middle is when the voltage on the left side, VA, you remember VA, suddenly drops from 400 to 380, 20 volts. Okay? So the PI shows all these long transients. Its current drops all the way to 16 and then takes long transient to come back. The optimal controller with very small transient keeps it very close to 20 with a small glitch. This one is the case that the voltage on the right side changes from 300 to 280. So again, the optimal controller has a very strong and robust response, but the other one takes long time to come back. Okay. Even I have given explanation why this happens. In other words, if you want to know why this happens. So I'm not going to explain in the class, but the explanation is there. Go ahead and read this couple of pages here. Yeah, I think that was it. No, it's not long. It's basically this page here. So go and read it, why this happens, this one and this one. Oh yes, if it, but you need to have add two sensors. Remember that, yeah. Oh yes, yeah, will be improved. I think so. Yes. Now you may be concerned about this. A little slower. This is due to the fact that in the optimal controller, if you look at the optimal controller structure, it's basically similar to PI. It's a PI. It's a P and an I. However, the P comes from the output, not from the error. In the conventional, the P also comes from the error. But if we change it from the error, in terms of responses, in terms of stability, nothing changes, but the responses will change. The general way is to do this. Here. So if you have K2, you can keep some of it here and push some part of it here. So let's say keep 50% here, push 50% here. Now, in terms of feedback loop properties and the poles and eigenvalues, nothing will change. But transient response will change because this system will generate a zero. So for that reason, I'm going to show you the responses. Here is the case that you put alpha equal 0. So all of K2 comes here. So you see the optimal controller becomes faster than the PI. If you choose it 50%, they are basically on top of each other. But the property, this property is still there. Okay. Now, my experience, we never care about this level of things that happening here. If you want to make the whole thing faster, we can make the whole thing faster. So here it was a question of comparison. So always in the problems that we have, in the converter designs that we have in this course, I'm going to use the structure, basic structures that we discussed about. I'm not going to change it. I will use this one. But that this discussion was only to show what is happening and how we can fix it if you want. Okay. Now, current limiting. Let's discuss this a little bit more because it's worth it. Current limiting, why current limiting is challenging? It's one of the most challenging problems in converter controls. The reason is this. This paragraph here basically explains. Let's say the converter is operating in normal condition connected to the grid, right? So this is the grid and this is the converter, the voltage of the converter. So these voltages are very close to each other and the current is flowing. But these voltages are very close to each other because the resistance is small. Now let's say this grid voltage instantaneously or transiently drops because we cannot really make it fast. Right? One solution is you need to increase the switching frequency to 10 kilohertz now. If you increase it to 10 kilohertz, probably you can address this one. But gain crossover frequency and phase crossover frequency, both of them become larger. For a phase margin, probably remains around the same number. So phase margin divided that frequency, delay margin goes down. So systems that are fast, control systems that are faster in these converters have lower delay margin. So you will face another problem. Okay, so how to solve really the current limiting? In other words, the current limiting can become really a big challenge. If you have limitations with your switching frequency, with the delay margin, and those things, it can become a big problem in front of you. You try to limit the current, you increase the speed of the current loop, and then you will see the system becomes unstable because the delay that it can tolerate now is not sufficient. So people have come with this partial solution and combination of these two solutions. What they do is, first of all, we design this controller. So try to make it fast again, and we will see the typical designs that we have. Now, if you take the grid voltage and pass it through a low pass filter and bring it here to the modulation signal with a proper gain, what happens is when the grid voltage suddenly drops, this modulation index also will drop. So this solution partially helps with that situation. Okay, got it? Okay, so this solution or this approach plus sufficiently fast current controller together for practical numbers of switching frequency can work together to limit the current. Okay, so let me show you a few simulations in order to understand this. Let's consider these 4 designs: design 1, design 2, design 3, design 4. This is slow, this is fast, this is faster. This is really the fastest probably you can get at 4000 kilohertz. Now, if you apply a grid fault, and grid fault happens at 0.15, right? Voltage short circuit. And the response of these 4 systems, when it is slow, it shows a huge amount of current transient, all the way going to 80 and then coming back. If you use the fast controller, it will go to 50 and then come back. If you use faster, it will go to 38 maybe, and if you use the fastest one, it will go to 30. Really the fastest one can only limit the current, but that fastest one will have other problems like delay margin and other things. Now let's look at this one. Yeah, delay margin that I said. Now intentionally go to the simulation and insert a delay to the control loop, and that delay models the delays of the digital control, because the controllers that I have here and the simulations you see are in continuous time, because these are easier to design them and simulate them. I did not use digital control. So whenever you want to include the delay of digital control, you need to go and yourself insert a delay. So I inserted 1 millisecond for the slow one. It can tolerate it with some oscillations, some big oscillations, but it can tolerate it to a certain extent. The other one, fast one, cannot tolerate 1 millisecond, can only maybe tolerate 67. And the faster one only 0.4, and the fastest one 0.22. So as make it faster and faster, the amount of delay that it can tolerate becomes smaller. And now here, if you add that feed-forward term, this is called feed-forward term. Commonly, this term is called feed-forward term because you take the grid voltage and add it not in the feedback, but as a feed-forward, you add it to the loop. It's not a feedback term. Okay, so when you add it, the feed-forward, you see the situation compared to this one is much better. This went all the way to 75 maybe, but this one goes all the way to, I don't know, yeah, 48 or something. So much better. And then the fast and the faster and the fastest. So together, if you design them together properly, you can make sure that you can limit the current. But still, current limiting all the time is a challenge that you need to go around it. And this is now when you apply the same amount of delays with the filter. Now the oscillations become smaller. Grid voltage support, I will talk in the next class. Okay, so let me see if I have time to go through one of the simulations very quickly. Sure. Mhm. No, because grid voltage, especially when we say grid voltage, AC grid voltage, but here in this case DC grid, always if you have a grid, that voltage is distorted, right? Is distorted, and then when you measure, it will be sensor noise anyway, but the distortions of the AC grid, harmonics, and those things. But DC grids are not very common, so we cannot say too much about that. But anyway, if you have a DC grid, we should expect to have distortions on the voltage of the DC grid as well. If that DC grid is connected to an AC grid through inverters, it will have oscillations, double frequency oscillations. Right? Yes, we need to put a filter to make sure that noises and oscillations, distortions, do not directly go to the control loop. Yes, yeah, you need to select that low pass filter properly, really. Again, the design of that low pass filter. Remember, why do we put that low pass filter? To help the current limiting, right? So, and remember, this is outside the loop, not inside the feedback loop. If it is inside the feedback loop, yes. Now, this is outside the feedback loop. If you put too much delay in that in that low pass filter, it does not help a lot, because you want, when the grid voltage drops, quickly come to the control system. So here I chose it 0.001 millisecond for the low pass filter, 1 millisecond. So, because we know, we just calculated that if you have 1 millisecond, the transient time of the system, we chose the poles about 1 millisecond, and we said that it cannot limit the current. So if you add that filter, it will help. You don't want to choose it 10 milliseconds, right? Or even a fraction of millisecond. A fraction of millisecond for current limiting is good, but it will have that problem of bringing the noise of the grid to the feedback loop. But if you mean by delay in the feedback loop, no. Here, the delay of the low pass filter does not go to the feedback loop. Sure. Right. No, that peak-to-peak ripple is not under control. In other words, it's yeah, average. Remember, in control, we are controlling the average, because everything is average. Those ripples depend on what? Two things: switching frequency, inductance. Once you choose those two, they are given. Right. No, no, you cannot, because it's not. It doesn't depend on control. Right. Yeah. Alright, so we have the file here. So this file is the file that compares the transfer function with the LQT. So we have this one, PI controller and LQT. So two converters and two PWMs here. We are using unipolar, and two controllers. One is using a PI and then one using LQT with two gains, 10 and 0.197. So okay. Now it's coming. So that shows the current of both of them, and disturbances happen. One of them here, another disturbance happens probably here.